This talk is about the Basel problem and the Riemann hypothesis. So what is this problem? How did it arise? And who solved it? What is the zeta function? And what is its link with prime numbers? And what is the Riemann hypothesis? One of the most famous unsolved problems in mathematics. But before I answer these questions, we should look more generally at infinite series. Look at this first series, 1 plus a half plus a quarter plus an eighth, etc., of infinitely many terms added together, where the denominators are the powers of 2. If we start adding up the terms one at a time, we get 1, then 1 plus a half, which is 1 1/2, then 1 3/4, then 1 7/8, and so on. These partial sums are getting closer and closer to 2. And in fact, we can get as close to 2 as we wish by adding enough terms. We say that this series converges to 2. And similarly, we can show that the second infinite series, 1 plus a third plus a ninth plus a 27th, etc., where the denominators are powers of 3, converges to 1 1/2. However, the series 1 plus a half plus a third plus a fourth plus a fifth, etc., known as the harmonic series, does not converge. It doesn't have a finite sum. And so by adding enough terms, we can make the sum as large as we like. To see why, suppose that this sum did converge to a finite sum S. Then the first pair, 1 plus a half, is larger than a half plus a half. The second pair, a third plus a fourth, is larger than a fourth plus a fourth. The third pair, a fifth plus a sixth, is larger than a sixth plus a sixth, and so on. Adding these new pairs then gives us 1 plus a half plus a third plus a fourth plus a fifth, etc., which is just our original sum S. So S is greater than S, which is impossible. And therefore our assumption that the series had a finite sum is wrong. There's no finite sum, and the series does not converge. But what is remarkable, as was proved by the 18th century Swiss mathematician Leonhard Euler, is that even if we decrease the sum by throwing away most of the terms, leaving only those with prime numbers 2, 3, 5, 7, etc. as denominators, there is still no finite sum. Let's now return to the Basel problem, which is about a different infinite series. In 1644, the Italian clergyman and mathematician Pier Mengoli, shown above, asked for the exact sum of this series, where the denominators are the perfect squares 1, 4, 9, 16, etc. This series does converge to a finite sum, and simple calculations show this sum to be a little more than 1.6. Indeed, we can see from this diagram that the sum is finite, because the area of each square, 1 squared, a half squared, a third squared, etc., is one of the terms in the series. And so the total sum is less than the area of the surrounding rectangle, which is 2 times 1, or 2. But what is its value exactly? At first, no one could answer this, not even Jacob Bernouill of Basel in Switzerland, shown below, one of the greatest mathematicians of his time. In 1689, he presented it as a public challenge to the mathematical community, and seeking the exact sum became known as the Basel problem. It was eventually answered in 1734 by Euler, who calculated that the sum of the series is about 1.644934, which he recognized as being very close to pi squared divided by 6. He then proved, in 4 different ways, some quite complicated, that pi squared over 6 is indeed the exact sum of the series, a remarkable result in that it involves the circle number pi. As Euler remarked, "Quite unexpectedly, I have found an elegant formula involving the quadrature of the circle, that is, pi." But Euler went much further than this. After proving that this sum, where the denominators are all squares, is pi squared over 6, he showed that when the denominators are all fourth powers, the sum is pi to the fourth over 90. When they're all sixth powers, the sum is pi to the sixth over 945. And when they're all eighth powers, the sum is pi to the eighth over 9,450. He actually went much further than this, correctly calculating the corresponding sums for all even powers up to the 26th power. But no one, even now, can say much about the sums for odd powers, even when the denominators are all cubes. Euler then introduced the zeta function using the Greek letter zeta, which for any number n is 1 plus 1 over 2 to the nth plus 1 over 3 to the nth plus 1 over 4 to the nth, and so on. It follows from the results above that zeta of 2 is pi squared over 6, zeta of 4 is pi to the fourth over 90, zeta of 6 is pi to the sixth over 945, and so on. It turns out that zeta of n converges for all numbers n greater than 1, but zeta of 1, which is the harmonic series we met earlier, which doesn't converge, is not defined. Euler next discovered a surprising link between the zeta function and prime numbers. As we've seen, zeta of 2 is defined as an infinite sum of terms adding to pi squared over 6. But as he proved in 1737, it can also be written as the product of 2 squared over 2 squared minus 1 times 3 squared over 3 squared minus 1 times 5 squared over 5 squared minus 1 times 7 squared over 7 squared minus 1, and so on, with one term for each prime number. So pi squared over 6 is equal to 4 over 3 times 9 over 8 times 25 over 24 times 49 over 48 times 121 over 120, and so on. Notice that we can use this result to prove that there are infinitely many prime numbers. For if there were only a finite number of primes in this product, then the product would be a simple fraction a over b, where a and b are whole numbers. But it's known that pi, and also pi squared over 6, cannot be written as fractions, and so the product must contain infinitely many primes. And in general, we have the corresponding product for any number n greater than 1. Zeta of n is the product 2 to the n over 2 to the n minus 1 times 3 to the n over 3 to the n minus 1 times 5 to the n over 5 to the n minus 1, and so on. So when n is equal to 4, as shown below, we have zeta of 4, which is pi to the fourth over 90, is 2 to the fourth over 2 to the fourth minus 1, that's 16 over 15, times 3 to the fourth over 3 to the fourth minus 1, that's 81 over 80, times 5 to the fourth over 5 to the fourth minus 1, that's 125 over 124, and so on. We'll now move on more than a century to 1859, when the German mathematician Bernhard Riemann wrote a groundbreaking paper. His paper was about the way that prime numbers are distributed, and his way into this topic was to generalize Euler's zeta function and its connection with primes. He found a way of defining the zeta function for almost all real numbers n, not just those greater than 1, and then for complex numbers. So before seeing what he did, let's digress briefly to how primes are distributed and to what we mean by complex numbers. On the left are the first few prime numbers, and already you can see that some primes are close together with a gap of just 2, such as 3 and 5, 5 and 7, 17 and 19, and 29 and 31, while others are more widely spaced, such as 23 and 29, and 31 and 37. We can plot these on a graph which shows the different jumps from one prime to the next. It's a rather jagged picture. But if we stand further back, we see that the overall picture is much smoother. To keep track of all these primes, we'll let P of x be the number of primes up to each number x. For example, P of 20 is 8, the 8 primes up to 20 in the first row, while P of 50 is 15, all the primes up to 50 in the 2 rows together. Below are the values of P of x for all the primes up to 100,000. It seems as though the higher we go, the more the primes seem to thin out, and this was made more precise in the 19th century when it was proved that, as x increases, the number of primes up to x behaves increasingly like x divided by the logarithm of x. This result is known as the prime number theorem. As mentioned earlier, Riemann extended the zeta function to almost all complex numbers. Complex numbers are objects of the form a plus b times I, where a and b are our ordinary real numbers, and I is the imaginary square root of -1. That is, I squared equals -1. We can then illustrate these pictorially by representing each complex number a plus bi by the point of the plane with coordinates a, b. So here, in the upper right, you can see the points representing the complex numbers 1 plus 2i and 3 plus I, while in the upper left is -2 plus I, and in the lower right is 3 minus 2i. We can now return to Riemann's zeta function. Using a mathematical technique called analytic continuation, Riemann showed how it can be defined for all numbers, both real and complex, except for zeta of 1, which, as we saw earlier, doesn't exist. For all real numbers n greater than 1, we get the same values for zeta of n that we had before. But Riemann's extended zeta function now has a value everywhere apart from at 1. Riemann's great achievement was as follows. He obtained an exact formula for P of n, the number of primes up to x, in terms of the zeros of his zeta function. That is, in terms of the complex number z, where zeta of z equals 0. So where are these zeros? It turns out that some occur at the even negative numbers -2, -4, -6, etc. But that all the other zeros appear within the vertical strip shown here, which contains all the complex numbers x plus yi, where x lies between 0 and 1. This is called the critical strip. Moreover, as we move away from the horizontal axis, the first few zeros, as shown here, occur at the points 1/2 plus or minus 14.1i, 1/2 plus or minus 21.01i, and 1/2 plus or minus 25.01i. Here, the real parts are all 1/2, and the imaginary parts, such as 14.1, are all given to 1 or 2 decimal places. So the first few zeros of the zeta function, now called the Riemann zeta function, lie on this so-called critical line where x equals a half. Moreover, if within this critical strip we move further up and down the critical strip, we find many more zeros of the zeta function on the critical line x equals a half. And we don't find any zeros off this line. This leads us to conjecture that every zero of the zeta function within the critical strip between x equals 0 and x equals 1 lies on this critical line x equals 1/2. Riemann considered this very likely, but didn't prove it, and it is now known as the Riemann hypothesis. So is it true? Or might there be some zeros lying off this line? For over 150 years, mathematicians have tried unsuccessfully to prove it, and to do so remains one of the most celebrated challenges in mathematics, with implications for other areas of the subject. It has been proved that, as we move up and down this critical strip, the first trillion zeros do indeed lie on this line, so it is surely true. But in mathematics, truth is absolute, and even just one rogue zero off the line would destroy the conjecture and cause havoc throughout the subject. I'll conclude with a surprising conversation that took place a few years ago. The American mathematician Hugh Montgomery, on the left, was visiting Princeton in the US and met the eminent physicist Freeman Dyson on the right over tea. In their conversation, he just happened to mention the gaps on the critical line that appear between the zeros of the zeta function. And Dyson replied, "But those are just the spacings that appear between the energy levels of a quantum chaotic system." If this analogy does hold, then the Riemann hypothesis may well have consequences in quantum physics, and it may be that quantum physicists, rather than mathematicians, will eventually be the ones to prove the Riemann hypothesis. And with that intriguing thought, I thank you for listening.